Good morning. I'm Al Avestruz. I'm a professor at the University of Michigan, and I'm here today to tell you how we can get solar panels to last from 25 years now to 50 years on Earth, and perhaps even more in space. Let me tell you a little bit more about myself. I graduated with my PhD from MIT. I got my master's and also my bachelor's there. And I remember kind of how this all started. So Arthur, who's my collaborator, and I were sitting at this huge round table in our lab. And we were just shooting around and just saying, how are we going to make solar panels better? So we thought about it a little bit. And in 2 weeks, we came up with a working prototype, and we submitted to a conference. So what I'm going to tell you about is what we've done since then and what we're going to do. So shade happens. So we know that solar has been just taking off. Thousands of megawatts get installed every year. And the Solar Industry Association says you get a 59% average growth in the industry every year. But there are issues. And what you find is that just a little bit of shading on a panel can cause really huge disproportionate loss in how much power output you get. And I'll tell you a little bit later on why this is the case. But if you look here, you can see that even a 9% amount of shading results in more than half the power loss, and even 3% results in a quarter of the power loss in a lot of instances. The other thing that shading does is it creates hotspots. The reason why is because solar panels wire their cells in series, and I'll talk about how that all works. What that does is, if some of the cells are shaded, what happens is that all the other cells try to push current through this off cell, and it heats them up. So what can happen is, because the cells are hot, you lose a lot of reliability, and you can even have a fire risk. The other thing, too, is because of all these issues with shading, what you get is that 75% of residential rooftops are not suitable for putting solar panels on. So this creates this very strained market in terms of where you can put solar panels. So in summary, shade happens. So you get energy loss, you get reliability risk, and you get this constrained market. So I'm going to tell you what we can do about this. Okay, so what we did was we have this chip, the SAGE chip. All right, what this does is it solves this series problem with solar panels. Okay, you're saying, if you get this Christmas light effect where you lose one, you lose the whole string. But you say, all right, well, why not just put it all in parallel? The issue with that is if you put them in parallel, you get a huge amount of current for the same amount of power, and your losses in terms of taking the power out and distributing it are very high. So we still need to keep it in series for the most part, but make it look like it's in parallel. And this is what the SAGE chip does. Okay? So it overcomes this weakest link thing that you get with a Christmas tree light. We do this without having all these extra inductors or capacitors, things you normally see in power electronics. What we do is we use the intrinsic energy storage, the capacitance, within each solar cell, which winds up actually being substantially large. So if you look at what panel level optimizers do, which is sort of the competing prevailing thing, is that if you lose part of your solar cells in a panel, you lose the whole panel. And when you string a bunch of panels together, which is typically what's done, you lose the whole panel, but the panels that aren't shaded are okay. That's an issue. So what we do is, in our technology, if you lose just part of the panel, you only lose that part of the energy. And so you still get most of the panel back. And so when you do a series string, everything's really okay. Okay, so how is our technology different? So this prevailing panel level power optimizer really is, we really differentiate from that. We get twice as much energy capture than a panel level optimizer. Compared to panel level optimizer, it costs 1/3 less per watt. We get higher reliability because we're doing cell level balancing, and it only occupies 0.1% or less of the panel area. So for space, what does this do for space? Well, you add a lot of resilience to shading and damage. So if you look at this illustration of the International Space Station, you can see there are a lot of communications, booms, a lot of structures that actually could shade panels. So this is useful. The other thing that can happen is that you can get mismatch as these things age. So you get varying degrees of degradation. So what you get is, over time, the cells become uneven. And what SAGE actually corrects for that. If you get a little bit of space debris and you lose part of a cell, suddenly that cell is mismatched, even if it's microscopic. And so space debris, micrometeorites, we actually add resilience to that. And so this means that you get a lot more lifetime performance, which means that you don't need as many cells for the life of the mission. So we have a lot of advantages over the competition, right? So there are different levels of how you can do this optimization, panel level, sub-panel level. We're very small, we're cheaper, and we get more energy out. So this is Mark, is a prototypical customer in our beachhead market, which is shaded residential rooftops. And that, is a $288 million per year market. And so what does he care about? He cares about cost of manufacturing, adding our SAGE device in, differentiation in this commodity market of solar panels, and he cares about reliability because of warranty costs. Okay. So we add a lot of value to Mark's customers. The balance of system costs are lower because the downstream power electronics are going to be cheaper. We get higher peak power point performance. We're going to be more efficient. We can cover more area because we don't have to worry about shading as much. Lower degradation and lower O&M costs. Point here is that the metric that counts is the levelized cost of electricity. And what we're trying to show here is that compared to just the central inverter, we can actually reduce this, and this is a conservative estimate, over 6%. So the market potential is just not residential rooftops. If you extend it beyond that to include commercial rooftop spaces and utilities, and you can argue that even though the shading is less there, what we find that even a 2% amount of shading, we still make a positive difference. So what this does is it extends this market to a $700 million per year market. So in terms of our financials, what we plan to do is, so we're going to be a fabless company. So basically, we're going to use a third-party fabricator for our integrated circuits, which is a typical model for our industry. And we plan to have cumulative sales of 1,500 megawatts or 180 million chips by year 5. And we want to have in year 5 a $33 million revenue with a 50% gross margin and greater than 20% profit margin in year 4. So Sage has actually, DOE has helped us a lot, okay? What they've done is they've de-risked this thing. So we have a Sunshot grant, and so this is sort of the major milestones. We're in 2018 now. We're getting first silicon that we are actually going to integrate into the panel in less than a month. And we're going to be going into reliability and also accelerated life testing, and do some limited field testing as well in this project. We're looking for $3.8 million. 600,000 of this is basically, when you make a chip, you get stuff that really works, you've tested it, you've done reliability things. Actually getting it to the point where it's an actual product actually is another step. And also packaging it as a product is also another. It's basically a manufacturing engineering step. We're looking for a series round of $3.2 million. And in the impact table, I'll tell you all about the specifics of what we're going to do with the money. But ultimately, what we want to be able to do is either merge into module manufacturers, just integrate as part of their thing, or be acquired by a large semiconductor company. So I told you a little bit about myself. Let me tell you a little bit more. So for 10 years before I went to graduate school, I actually worked in industry and for startups. So I have some experience. Arthur, who's my collaborator, is also an MIT PhD, Caltech, master's and undergrad. So I think what we would do is we would form the leadership team, and we would have to grow a team for both management and also a technical team, so a CEO, a CFO, and so forth. So what's our dream? Our dream is to put a solar panel on every rooftop. Someone pointed out that this thing over here, this house has a tree. And so the tree has no solar panel, right, because of shading. So in a sense, we don't want to trade trees for solar panels. And I'd like to acknowledge the Department of Energy, Sunshot Initiative, and all the disclaimers that go along with having that project. And I'll be happy to take any questions.
Could you talk about how the chip works and how it's configured? Is it one chip per cell?
It's one chip for every 3 cells right now.
Okay.
And perhaps we can do more cells in the future.
Right.
But right now, what we have is basically 3 cells as one chip. So we're talking about adding 5 cents per watt, basically, to the cost of the panel.
Is the chip connected in parallel to the cells, for example?
I can show that at the impact tables. I have a slide to show exactly. There's a paper out on it. It's not quite in parallel. It's a ladder structure, actually.
Can these be applied as a retrofit or?
To existing cells, to existing panels. You'd have to deinstall them. Can it be done in the field? Possibly. Possibly if you had something automated to do it, which is kind of what we're thinking of doing as part of that 600K, possibly. It's actually, it turns out it winds up being just sort of like the final step. So we spend a lot of time figuring out how do you integrate this into an existing solar panel process, manufacturing process. Turns out if you just kind of like don't do the end connections, and then you can just basically just go across and slap these on and bar solder these down. So it is a possibility. I think it requires us to think about it more.
So you had the example where 3% shading and was 25% reduction in power.
That's pattern dependent. Yes.
Have you done with your chip, have you actually measured what the power reduction was compared to that?
We did. So we have that in a paper actually, where we actually show that. Well, yeah. So we actually show that if you don't do anything about the shaded cells, and the thing is, the way the panels are wired is they're split up in sort of these 3 sections. right? So if you shade it just the right way, you lose a whole section. And so that's been kind of it's been demonstrated.
So this is really cool, and I think the question about retrofit is an important one relative to NASA. So you're right, the International Space Station with all the booms and the, you know, where the sun is with respect to it, we actually have a very complicated code that figures out what the power level is going to be throughout a mission so that they can determine which experiments people can do. So I don't think you can probably retrofit the station power system.
I don't know how the panels are made,
Yeah, they're
but with
they're pretty old.
robotics, maybe.
Ooh, okay, so well, we can talk about that. But the next question is, and this is something I don't know, Earth orbiting satellites, is there a lot of are there shadows that occur?
Depends where your altitude in your orbital path.
Okay. So for future NASA activities, it might be very beneficial to add this, depending on what orbit we're in and what.
It's all or none when you have that, obviously.
Yeah, right. So this might not help, right? So it's either all dark or we don't have a
Lunar
branch or
surface.
something. Huh?
The lunar surface could be a problem for shadowing with the terrain.
That's right. Yeah, that's right. Lunar surface might be a good, yes, if we use solar panels on the lunar
It's
surface.
kind of a niche application.
Dust helps with dust
Yeah,
a
yeah,
lot.
yeah. That's a good point.
Or I would think if there's failures at certain
Yep.
cells and stuff like that, it's still a valid.
Well,
Yeah.
I would want to know, I'm sorry.
Thank you. No, go
Therese,
ahead. No, that's helpful.
So when they're fully illuminated, do these chips cause any losses?
So we figured out a way that when they're fully illuminated, basically you get like over 99.9%. Like the standing power loss is really, really small. We figured out a way to do that. Originally we didn't, but in the last 6 months we're like, oh, we know how to do this. Yeah, we can make it so that almost across the board the efficiencies, so it's almost not there when it's fully illuminated.
How are they integrated? Are they laminated into the idea that you would laminate them into the array, or would they be like a bus bar?
So basically we would put it on an expensive flex circuit as a package, and the chip is in there, and you just slap it down, basically across the cells. So it would connect to the bus bars. Basically, we would bar tack to the bus bars from the back, not the bus bars, the interconnect.
Are there any durability changes that?
That's where I'm going with that.
By doing
You're
that.
putting a lot of chips and a lot of new electronic components into a module.
So yeah, we have to test for that, right? But it turns out these chips are very simple. It's all open loop. It's intelligent power, but not very intelligent. So it basically kind of runs itself. And so we're designing it so there are actually not a lot of failure points. We've also come up with some new ways to actually have these chips have redundancy actually, where basically if you lose part of the chip, it still operates fine. And you can add something where if you lose a cell, you can actually bypass it. So there's a few things we're kind of thinking of adding on, but these are sort of like later on.
So I was going to ask if this chip is useful for thin film solar. If you had like a first solar panel where the wiring is different than what you have here.
For different types of, so it's going to help with any kind of solar technology, right? So any kind of cell. So this is going to work.
How would you insert that in one of those?
We'd have to think about how thin film would work for us. We haven't really thought of it enough yet in terms of how we interconnect into them. But anytime you have multiple cells in series, whether they're multi-junction or gallium arsenide or anything, this makes
series and parallel, right? It's
right.
Complicated. So shading is maybe less damaging because current can find different paths to.
Yeah, but maybe it doesn't have to be as complicated to wire it up, right? If you use a ladder structure, that's what I'm saying. You can. So sometimes if I'm imagining what's happening with the thin films one, is they're making it so that it sort of like snakes around, right? And it's kind of like in semiconductors, they call it common centroid layouts or things like, basically the layout makes it so it's resilient, right? But it's complicated, right? So that means on average the path lengths are longer, so maybe you get more resistive losses. What this does is it actually lets the path lengths be very direct and shorter. So in that sense, it might actually help a thin film panel.
So the other question I have is this IC, is that made in a BCD technology? Is it the 40 volt, 30 volt, 20?
It's not. It's low. It's the cheapest 180 nanometer CMOS you can get. We found the cheapest possible one. Went to just great lengths to just make that work because it's the cheapest, most common process. They tape out like once a week. It's just a massive volume thing, and we're going to try to leverage that.
So why do you need so much money? The chip is, you already designed something, and it's cost pennies to make. The packaging is pretty straightforward. It's going to go in some plastic overmold package,
Yeah.
maybe, and that's also pennies per.
It is, but taking something and going to a product, proving out the yield to really statistically significant things. So going to a chip, like going commercially with a chip, it seems like, oh, you already have a chip design. But going from a university lab to something where you're making tens, hundreds of millions of, it is something. You require really some IC designers that have been doing it a while. There are some things you just have to be done.
So what are your top three concerns with your chip?
Um,
Well, why would the yield be? It's a simple chip. Why would the yield be bad? It's 180 nanometer CMOS.
So here's what we're doing. We're running 10 amperes into a standard CMOS chip, right? And that's not typical. There are things like there might be local hotspots on the chip we haven't been able to look through. So there's some details that, this thing has to last 50 years. Even deciding how do you test for something like that is also a big deal, right? What does it mean to do accelerated life testing for something that's going to have to go 50 years? So there's some of that has to be figured out.
Yeah, I guess another question. So you show some scenarios where a bird poops on it, or or it's behind a tree because it's in a
cloud. Yeah.
I'm curious, where would you focus this? I mean, would you focus it for the rooftop market? My assumption is that the shading losses associated with large scale utility are minimal, right? By comparison.
By comparison, yeah. So that's true. So our beachhead market is where the biggest problem is, which is residential. But in terms of utilities and commercial rooftops, so even if you get a 2%, not just shading, but mismatch, right? We still make a difference. So one of the things what can help in manufacturing, for example, is doing sorting and binning. You may not have to do that. If you have a crack just transporting a panel, if you're willing, you can actually live with that crack. So maybe the cost of transportation goes down or returns or things like that. And if you have large installations, I bet you a good portion of it just comes broken.
Or installers walk on them while they're installing.
Yeah, well, it does. They do that. And so tons of stuff come back, right? So if you're willing to, discount, let's say, okay, I don't have a full 300 watt panel anymore. I'm at 280 because I cracked a few cells. Well, it's still a usable panel, right? In terms of utilities, it gets dirty, right? And if you look at them, they'll shade so that over time, the lower sets will actually have less UV degradation than the top. And so they're now mismatched. So we deal with that as well. So I think it's gonna help across the board.
So I guess I have a quick question about your fabless production concept.
It is fabulous, yes.
Okay, can you talk? It's fabulous, right? Can you talk a little bit more about your thought process on your plan? Because it sounds like there's some complication in something that's very simple. Have you already identified partners, et cetera?
There are a couple of South Korean companies we're kind of looking at that can do fab for us and things like that. We're trying to find an inexpensive, leverage kind of high volume fabrication process and just piggyback on that. And then as we make more chips, actually we can drive our own market as well. But yeah, we're looking at, there's a lot of people that do 180 nanometer. CMOS, this is a standard CMOS. Nothing really fancy about it. We try to find the least fancy thing possible, right? Yeah, we're looking at it. I mean, it's going to take a little time to figure out who the right people to work with are.
Then it sounds to me like you may actually have a secondary panel market that you may be enabling. I'm wondering if you've explored that at all. This idea of cracked panels, less efficient panels, old panels, and perhaps almost creating a secondary market, is that?
I have to think about that. That's possible, right? Like where, kind of like your bargain basement panels, right? These are kind of like your, kind of the rack where there's a little bit of a thing broken. Yeah, it's possible.
Just relative to space applications, a lot of our arrays are not similar to, and this might not, I'm just wondering if we can include it into the market for space applications. We have rollout solar arrays, and so I don't know if we would interrupt production, and I'm just looking at the NASA case, right? So I'm just not sure that it's the same as terrestrial kind of photovoltaics and how we would modify those, and that you would use the cheapest chip from South Korea.
I would look way more carefully, definitely, at that. And I may not use the cheapest chip from. Well, we may use the cheapest chip, but we may sort them, and
yes.
You know what I mean. And
so it might be worth looking into, though. I think that the weight and the manufacturability of what we use on space systems in general is probably different, and so relative to the application for space applications.
And I would love to work with NASA on looking at that for sure.
Thanks. Thank you.
And I guess on that note, the components you're putting in there, the rad hardness of
Yes.
the chip.
That has to be also considered as well. So this idea that we're doing, where we're doing kind of redundancy, we kind of thought about look, that's by adding that for the last 50 years, you gotta kind of think about that, right? Like there has to be some type of smooth failure mechanism and just smooth degradation and redundancy.
That's good.
And that's time.
Thank you. Thank you very much.